Good morning, class, and welcome to this lesson on Magnetism 1, Basic Magnets. Today, we will know some basic information about magnets. Okay, so we're just going to cover the basics before we get into the heavier math and the more the high-level stuff here. Okay, so first thing, just very similar to electric fields, very similar to electricity. Magnets follow the same basic rules. Like poles repel, unlike poles attract. So if you put a south pole and a south pole and magnet together, they will push each other away. North and north will push each other away, but north and south will be attracted to each other. So likes repel, opposites attract. Okay, same basic rules, electricity, not very difficult. Okay, so that's a magnet. Oh, and by the way, all magnets have a north and south pole. All magnets have a north and south pole. We'll get to that in a second. Second thing, when drawing magnetic fields, all magnets have a field around the magnet. You can see that from this picture. These lines represent a magnetic field. Now that's not saying, these lines aren't saying that there's no magnetic field, say, in this region right here or in this region right here. Okay, the magnetic field exists everywhere around the magnet. It exists everywhere around the magnet, but we just draw only a certain number of lines because there's no point in drawing just a mass of lines there. Okay, so magnetic field lines are drawn, always drawn, from north to south. They are always drawn from north to south. Every magnet north to south. Okay? Doesn't matter if it's a bar, like the horseshoe magnet like this or a bar magnet like this. All magnetic field lines are drawn north to south. That has some interesting implications because, as we know, a compass, if we have a compass, it'll point to the North Pole. So all compasses point to the geographic North Pole. Okay? But when we draw our magnetic field lines, a compass will always point from north to south. So a compass is always going to point to the south pole of a magnet. As many of you know, Earth is a giant magnet. Earth is the biggest magnet we can think of. Okay? And because Earth is a giant magnet, what that means is the magnetic south is the same as the geographic north. Okay? Because magnets point from north to south, that's our convention. It's our convention, just like electricity. We have certain conventions for things. The magnetic south equals geographic north. Because a compass will always point, a compass will point along magnetic field lines. A compass will point along magnetic field lines, and we know that magnetic field lines are always going to be pointing from north to south. Okay? There's no such thing as a single pole magnet. Okay? Or a monopole. Okay? At least not in this basic physics course. I'm not sure about advanced theoretical physicists in universities, but for AP Physics, there's no such thing as a single pole magnet. If you break a bar magnet in half, you will have a new north and south, north and south. It doesn't matter how many times you split it in half, you're always going to have a north and south pole combined with one another. Okay? And we can see that from maybe this picture right here. This is an example of what a magnetized and unmagnetized piece of metal looks like. Basically, inside certain metals, we have what are called magnetic domains. We have magnetic domains. And these are clusters. These are clusters of aligned atoms. These are clusters of aligned atoms. So each of these arrows represents a magnetic domain. Okay, so like this is a magnetic. These are all magnetic domains here. Okay, and there's a whole lot of atoms, thousands or millions of atoms that are all aligned to each other. Okay, so this would be an unmagnetized piece of iron. Okay, all the magnetic domains are pointing in random directions. As you can see here, the magnetic domains are starting to align themselves to each other, and this would be a full-on magnet where all the magnetic domains are now all aligned with each other. Okay, so when the magnetic domains align, when the magnetic domains align, we have a magnet. We have a magnet. Okay, this is a regular piece of iron becoming a magnet when all the magnetic domains align. Okay, and if we break this magnet in half and have these two here, we will have equally strong magnets. We will have equally strong magnets as the original magnet. Okay, so as you can see here, these magnetic domains, they're represented by an arrow. They're represented by an arrow. Okay, and an arrow is just a model. Okay, it's just a picture we use to understand it ourselves. But every single arrow has a tip and a tail. A tip and a tail, right? A head and a tail. So if every single arrow has a head and a tail, essentially that's like saying there's a north and south pole for every single magnet. And that is why we can never have a monopole, because even if we split them up and split them up, there's still magnetic domains inside these things. And we get these magnetic domains, we still have an arrow. We still have a head and a tail. And so no matter how many times you split it up, there's always going to be a front end and a back end, okay? Or a north and south pole. Okay? So those are just some basic facts about magnets. I can't say if they're going to likely to come up on a test or not. Definitely likes repel and opposites attract is going to come up again. But those are just some basic things to get us started. So when we start seeing pictures of magnetic fields and magnetic domains, we know how to draw them and we know what we're looking for.